Hello everyone, welcome back to the lecture series on fundamentals of generative AI and large language models. In my previous session, we have discussed about the mathematical foundations that are required for understanding diffusion probabilistic models. In today's session, we will discuss about denoising diffusion probabilistic model, and we will look into only the forward diffusion process. Okay. So, we will start with what is denoising diffusion probabilistic model. Okay. So, denoising diffusion probabilistic model, or we call it as DDPM, it is a specific formulation of diffusion probabilistic model. Okay. So, it came into picture through the paper Denoising Diffusion Probabilistic Models by Jonathan Ho and the team from UC Berkeley in 2020. So, we will see what is this DDPM and how in this DDPM how the forward process happens. Okay. So, we all know that in any diffusion probabilistic model we have the forward diffusion process and the reverse diffusion process. Okay. So, in the forward diffusion process we start from a clean image and then we keep on adding noise subsequently for a number of steps till we get almost pure noise. Okay. So, this is clean image to complete noise conversion that we do in the forward diffusion process. And in the reverse diffusion process, we start from almost pure noise and then go through several steps till we come to the clean image. Okay. So, this is known and this is fundamental of any diffusion probabilistic model. Now, we will see what is the mathematical formulation for forward diffusion model in denoising diffusion probabilistic models. Okay. Now, in one of my previous lectures, I have introduced you all to what is Markov chain. Markov chain is basically, or Markov chain states that what will be my next state depends only on my current state, not on all the steps that have led me to the current step. Okay. So, that is Markov chain, and our forward diffusion process is modeled as a Markov chain. So, we have real data which is our image, then it is run through t steps of denoising and every step is more noisy than the previous step. Okay. So, this we have seen. Every step when t equal to 1, 2, that time the noise added to the image is much lesser compared to when we have t equal to 30 or 35 or 40. So, as and when the time progresses, the time stamps progresses, the amount of noise that is added to the image keeps on increasing, and finally we get a complete noisy image. Okay. So, if we have x t minus 1 this image, x t will become this one, and this is the conversion. There is noise addition from x t minus 1 to x t. Okay. Q x t given x t minus 1 is the probability of getting x t given x t minus 1. So, what is the probability that I get x t given I know that this is my x t minus 1, this is given to me. So, what is the probability of getting a noisier sample from a sample which is less noisier, okay? And that is given by this probability distribution. Okay. Now, this x t is sampled from a Gaussian distribution with mean mu and covariance sigma. Now, when I tell this one, because the forward process, it is a fixed process, there is nothing, no learning happens in the forward process, we consider it as a predefined Gaussian distribution. The probability distribution is can be thought of a Gaussian distribution with mu and covariance sigma, and it is written as n within bracket, this is x t, which is your sample that you have sampled out, and this is mu is your mean and sigma is the covariance. So, that is how mathematically we write a or we represent when a sample xt is taken or xt is sampled from a Gaussian distribution with mean mu and covariance sigma. So, that is the mathematical way of writing. Now, we will look into more details into the maths that is involved in the forward diffusion process. So, we know this is the probability distribution of xt given xt minus 1 equal to this n, xt is sampled from this distribution and this is the mean and this is the covariance. Okay. Now, this is forward diffusion distribution as I told, this term is the covariance term. In forward diffusion process we have this equation. Okay. Now, if you see what exactly this covariance is giving, the covariance describes how uncertainty is distributed across the dimensions and how different dimensions are related. Okay. So, we have in our previous lecture we have discussed what exactly covariance is, and here we are using that covariance to understand the uncertainty associated with the noise across the dimensions and how different dimensions are correlated. Okay. So, this is just once more I have written the covariance term can be written if there are two variables x1 and x2, this is written as variance of x1, covariance between x1, x2, covariance between x2, x1, variance of x2. This is for two variables x1 and x2. So, x1, x2 if it is like that, if your x is like this. Okay. And zero covariance means there is no relationship between the dimensions. Okay. This we will keep it in mind. Now, in this covariance term we see it is written beta t into I, okay, where beta t is the magnitude of the noise. Okay. We have seen in our previous discussion also beta t was deciding how much noise will be added to the forward diffusion process in a particular time step t. Okay. And what is I? I is basically the identity matrix. Okay. It is written as like this. Now, beta t into I, if we do a multiplication like this is matrix, and then we get beta t 0 0 beta t. So, this is my beta t into I, which is basically my covariance term. Okay. Now, in the forward diffusion process, again I have written that same equation. This is the probability distribution of getting xt given xt minus 1 or conditioned on xt minus 1. So, your xt is conditioned on what your xt minus 1 is having, how much your xt minus 1th step image, how much noise it is having. Based on that one your xt will be made, how some extra noise will be added to it. Now, this xt is sampled from that distribution. This term is the mean, because we know that is the way we write in terms of Gaussian distribution n xt. This term becomes the mean and this is the covariance term. Now, if you see once again I have written xt is the image at time step t, xt is the image at time step t, t is missing. Okay. Xt minus 1 is the image at time step t minus 1, I is the identity matrix and beta t controls how much noise is added. Okay. So, till this one I hope it is clear. Now, given the previous image xt minus 1, the next image xt is sampled from Gaussian distribution with mean square root of 1 minus beta t into xt minus 1 and covariance beta t into I. What exactly it means? That I have an image at the time step x at the time step t equal to at the time step t minus 1. Okay. So, how will I get xt from this xt minus 1? So, once I have the previous image xt minus 1, the next sample xt, it is basically sampled from the Gaussian distribution with this mean This is the mean and this is the covariance. So, I have a Gaussian distribution having this mean and this covariance beta t into I and mean square root of 1 minus beta t x to x t minus 1, and there from there I sample x t. Okay. Now, if you see, the mean is a scaled version of the previous image. What do I mean by that? This is x t minus 1, basically it is my previous image. So, this is my previous image. Correct? This is my previous image. So, x t minus 1 into square root of 1 minus beta t, that is the mean. So, the mean is a scaled version of the previous image and the scaling factor is root over of 1 minus beta t, where beta t varies between 0 and 1. Now, the next question is, why such a scaling of the signal strength is required? Is it required, or if it is not there, what will happen? Okay. So, that we will see little later. Again, I have written the same equation here because we are this is the primary equation for the forward diffusion process. So, I have kept it here, and then what I have done is let alpha t equal to 1 minus beta t. So, there is a substitution that I want to do here, and I have rewritten this equation q x t given x t minus 1 is equal to n x t. X t is sampled from this distribution with 1 minus beta t is alpha t. So, square root of alpha t x t minus 1 and 1 minus alpha t, because this is beta t. So, alpha t equal to 1 minus beta t. So, beta t becomes equal to 1 minus alpha t. So, 1 minus alpha t into I. Okay. So, this is in terms of alpha t. Now, a sample from here can be written, the sample is x t, can be written as x t equal to square root of alpha t into x t minus 1 plus square root of 1 minus alpha t into epsilon t, where epsilon belongs to a distribution with 0 mean and variance 1. Now, how I have written this one? Any sample can be written as this is basically your mean and this is basically your covariance. Okay. So, it can be written as the mean plus standard deviation. From that idea, this has been written as the mean plus this is the standard deviation. Okay. And with epsilon 2 which belongs to a distribution with Gaussian distribution with mean 0 and variance 1. Okay. Now, this is basically your scaled signal strength, that is how much of information was there in the image. A scaled version of that one is this this term, and this is the noise term. Okay. Because epsilon t is taken from a random vector from Gaussian distribution, standard Gaussian distribution. Now, this is, the signal is scaled with square root of alpha t. Okay. Now, what happens if the signal is not scaled? We will see that one. Okay. So, here we have seen it is scaled to with square root of alpha t. Now, if I have x t equal to x t minus 1, which is my complete previous image, plus square root of 1 minus alpha t into epsilon t, then what happens? If I take variance of x t, I can write equal to variance of x t minus 1 plus variance of this term. So, I will write it here, variance of x t equal to variance of x t minus 1 plus variance of square root of 1 minus alpha t into epsilon t. This I can write as variance of x t minus 1 plus variance of a into epsilon t, where a equal to square root of 1 minus alpha t. Now, we know this will remain as same, x t minus 1 plus a square variance of alpha t. Okay. So, this is becomes variance of x t minus 1 plus alpha square means a square means 1 minus alpha t, okay, then variance of t. Now, this variance of epsilon t is 1, so we can write it like this. Okay. Now, so what happens is, if I take the entire previous image, what happens there? The variance grows. So, this variance of x t minus 1, it keeps on growing, and after many steps the variance would become very large and the distribution will blow up. So, this is the problem if we take the complete image. So, that is complete image of the previous step. That is the reason we take a scaled version of the previous image. We have taken this expression x 1 equal to square root of alpha 1 x 0 plus square root of 1 minus alpha 1 into epsilon 1. Now, if we expand it recursively and we try to get what is my x 2. So, I will write it here, x 2 equal to square root of alpha 2 x 1 plus 1 minus alpha 2 epsilon 2. Now, that I can write it as square root of alpha 2. For x 1, what we will write? Alpha 1 square root x 0 plus square root of 1 minus alpha 1 epsilon 1. This is my x 1 term, this is basically my x 1 term, plus 1 minus alpha 2 epsilon 2. Okay. Then I can write this one as square root of alpha 1 alpha 2 x 0 plus square root of alpha 2 1 minus alpha 1 epsilon 1 plus square root of 1 minus alpha 2 epsilon 2. Okay. Now, this term is actually having your signal information. So, this is this contains original signal, correct. What is our original signal? That is my x 0, and this term is a Gaussian noise term. This is also another Gaussian noise. Okay. So, can I write it like x 2 can be written as square root of alpha 1 alpha 2 x 0 plus sum of Gaussian noises. Okay. Now, if I make, let us consider alpha 2 bar equal to alpha 1 alpha 2. So, and let z equal to addition of these two Gaussian terms, which is square root of alpha 2 into 1 minus alpha 1 into epsilon 1 plus square root of 1 minus alpha 2 into epsilon 2. Okay. So, since epsilon 1 and epsilon 2 are independent Gaussians, its covariance can be written as alpha 2 into 1 minus alpha 1 I covariance plus 1 minus alpha 2 I. That is, if I do the calculation, alpha 2 minus alpha 1 alpha 2 plus 1 minus alpha 2 I, that is equal to 1 minus alpha 1 alpha 2, that is 1 minus alpha into I alpha 2 bar, because this is my alpha 1 alpha 2 into I. Okay. So, if we do it like this, we are getting x 2 equal to x 2 bar x 0 plus 1 minus alpha 2 bar into I. Okay. So, this is the expression for x 2. Okay. Now, we will see the same thing I have generalized here. So, x t bar equal to product of s equal to 1 to t alpha s. Okay. So, that alpha 2 bar I have generalized and I have written it like this, x t bar. Okay. Therefore, alpha 1 into alpha 2 into alpha 3 dot 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 alpha t can be written as square root of alpha 1 into alpha 2 into alpha 3 dot 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 alpha t can be written as square root of this product term. Okay. Now, I can write the probability distribution for the forward diffusion process q x t given x 0 equal to n x t. This is what has come there as the mean, square root of x t bar x 0, and this is the covariance. This is the mean and this is the variance, the covariance. Okay. Now, till this one we have seen how we have written the forward diffusion probability distribution equation for the forward diffusion process. Now, we will learn something which is called as reparameterization trick. What is that one? And it is a very, very important concept in denoising diffusion probabilistic model. Okay. So, we will see. Now, suppose we have Z which is sampled from a Gaussian with mean mu and variance sigma square, then instead of sampling Z directly, we can write Z equal to mu plus sigma into epsilon. Okay. This is exactly what we were doing in the previous step also. So, the same thing here we are reinforcing, and we will see how with clarity what exactly it is coming out from this reparameterization trick and why it is important. Okay. Now, Z can be written as the mean plus sigma, which is your standard deviation, into epsilon. Epsilon belongs to n01, which is a distribution with Gaussian distribution with mean 0 and variance 1, which is basically your standard Gaussian. If I apply this idea, then I can write q x t given x 0 equal to if we apply this idea to this equation which I had written before, I can write it. So, here my mean becomes, this is my mean and this is my variance term, okay, or covariance term. Okay. I can write it, or I can sample x t as square root of, that is the mean, this is basically your mean, plus this is my sigma because square root has come. So, this is my sigma into epsilon. So, what we are getting from this equation is I can get x t given I know the initial image x 0 at any time instant t. So, this is a very important concept of denoising diffusion probabilistic model. So, what happens is, this is basically your remaining signal strength and this is your accumulated noise. Okay. So, without the reparameterization, if we require to find out xt, I have to go from x0 to xt in several steps, x0, x1, x2, x3, x4 till xt. It requires T diffusion steps. Okay. With this reparameterization technique, xt can be obtained directly in one step for any random step t, provided you know x0. x0 is known to you because that we have given to the model. So, this is the way where in one step we can get xt and we can avoid going through all the steps in the diffusion process. Okay. So, with this one I come to the end of today's session. Let us, before I conclude, let us have a quick look on what all we have studied today. So, we are studying the forward diffusion process in denoising diffusion probabilistic model, which is a specific framework of diffusion probabilistic model. Okay. So, here also we have the forward process and the reverse process. The forward process is a known process. There is no learning that happens in the forward process. It is considered as a predefined Gaussian, and then what we have tried to see from there is how the mathematical expression of the diffusion of the probability distribution is written in terms of mean and covariance, and the mean was a scaled version of your previous step image. Why that scaling, how that scaling helps, also we have seen if the scaling is not there, then the variance will blow up, the variance will keep on increasing at each and every step and the distribution will blow up after several steps. Okay. So, we have the mean as a fraction of the previous image and we have a covariance term with that one. Now, we have seen how we can write that one in terms of there are some mathematical steps by which we have seen the reparameterization trick, which allows us to get a sample xt from xt, t being any specific time step, if from only the original image. It does not require for us to go through the entire t number of diffusion steps to get xt. Okay. So, there are couple of mathematical steps that we have done and we have seen how this reparameterization helps in speeding up the process. So, at any instant of time you want to see how much of what is the noisy image that you are getting at t equal to 99 say. Then once you have x0 with you, you can directly from x0 you can find out what will be the form of x99. Okay. So, that is the, and it is a very important concept in DDPM or denoising diffusion probabilistic model. Okay. So, with this one I come to the end of today's session. I hope you all have got some understanding about the forward diffusion process, the maths behind the probability distributions behind forward diffusion process. In my next class, we will discuss about the reverse denoising diffusion, denoising process or reverse diffusion process, in which the actual learning of the neural network happens. There will be parameters associated with that process, and we will see what are the mathematical formulations of the reverse process in my next class. Okay. Till that time, till we meet for the next session, keep learning, happy learning, and thank you all.